Hello, everyone. Welcome to the session about embracing resilience in GraphQL. It's crowded today. Thank you, everyone, for joining this session. Today, we're going to talk about the cache avalanche effect and what we did to deal with this situation. Short words about me. I'm Fernando. I'm originally from Argentina. I'm a team lead in software engineering at Joyn. I've been in software for around 12 years already. In the last years, my focus has been in teams dedicated to backend engineering and mostly dedicated to resiliency around distributed systems. A word about Joyn. Joyn is an entertainment platform that offers a free product with vast content on live TV and also on video on demand. It offers content from ProSiebenSat.1 and also from a lot of other content partners through a single platform. And finally, like users can also choose to pay a monthly subscription to get access to pay the live TV channel and exclusive content through what we call the Joyn Plus product. So this is a very high-level overview. This is a very simplified version of a part of Joyn's architecture, but this can apply to a lot of other platforms out there, right? On the left side, we have our clients, our mobile platforms, our web platform, our smart TVs that communicate through the backend and send requests to the backend. These requests go through a gateway. The gateway can do some authorization tasks, check the tokens in the request. You can have also some CDN caching happening on the gateway. And then the requests go through to our GraphQL server. GraphQL server sits behind a load balancer and can scale up and down according to the traffic that we are having at that moment. Unfortunately, we don't have enough time to do an introduction to GraphQL, but GraphQL is a query language with which the clients can send one single request and request all the data they need without overfetching and receiving that data in one single request. For that, GraphQL needs very often to communicate to a lot of downstream services to collect this data, aggregate it somehow, consolidate it, and send it back to the clients. Since GraphQL needs to talk to a lot of these downstream services, it's very often to put a cache instance like next to GraphQL. And the strategy that is usually used for this is the cache aside pattern, right? How does this work? So first of all, we try to read from the cache. If it's a cache hit, we just return this result to the clients without actually making a request to the downstream services. If it's a cache miss, which means that the cache entry is not in the cache, we go to the downstream services, to the data sources. We receive the data from the data sources, and finally, we store it in the cache with an expiration time. The expiration strategy we were using here is a simple TTL-based strategy. And this strategy can take you really far away, like can have a massive and very good impact on your latencies, especially on your non-tail latencies, right? Like P50, P75, especially if you have a reasonable cache hit ratio of around 80, 85, 90%, these latencies will decrease a lot, right? Like this strategy can be very effective. Tail latencies like P90, P95, P99 are very difficult to tackle with this strategy because they usually fall into the cache misses, right? So this works quite well. But now let's think what happens if there's something going on with the cache instance, right? As we said, the cache is kind of protecting the downstream services. It's kind of absorbing all the requests that should go to the downstream services. It's being absorbed by the cache. So what happens now is, by any reason, we can go into more detail later how this can happen. What happens if for some reason the cache is not responding to you, right? It's all the instances are cache misses. I see some smiles. Maybe some of you already faced this situation. Spoiler alert, it's not a nice situation to be in. What happens now? Suddenly you have a massive increase on the requests that you're sending to your downstream services. This can be a database, a service, like whatever, right? Since the cache was holding on and absorbing all these requests, if it's down, suddenly all the requests go to the downstream services. And then you have an issue on these services, right? Like then it's not a nice situation. Why? Because the services will scale to handle a much lower traffic, right? Before the cache goes down. So this is called the cache avalanche effect. Yeah. As I said, it's not a nice situation to be in. I've been personally involved in incidents on this type. And the word avalanche, it's something that resonates a lot with me, and because it's so accurate on the feeling that you get when you're looking at the dashboards on these incidents, and suddenly the requests go up by a huge factor, and you feel that you're getting bombarded by these requests, right? So what is the cache avalanche effect? It's like, of course, when there's a massive, by any reason, and sudden and massive increase in the cache misses, which cause an unexpected high load in any downstream service, which affects your latencies and the overall health of your service. Like, how can it happen? I'm going to go quickly over each of these points. The most obvious one, the first one, is the cache is really down. Infrastructure-wise, you have an issue with the cache. By any reason, the cache is not always to respond. Therefore, you treat every request as a cache miss. And the other ones are not so obvious, right? Like this, the cache response maybe has a higher response time, and it's actually exceeding the threshold that you yourself put as a timeout for the request that you send to the cache. Then it's not that the cache is down, it's just that it's a little bit degraded, but since your timeout value is very strict, you're treating these requests as cache misses. The other reason is that it simply struggles to accept new connections. This can happen ironically when you most need it, when you're scaling up massively, and then you suddenly have a lot of new tasks, new instances that try to connect to the cache. You might face a situation in this case when the cache is not able to accept these new connections. The cache is full, simply full. You cannot put more stuff into the cache, and therefore on the step number 5 of the previous slide, you cannot put new stuff, and therefore that entry is still treated as a miss. Right? And finally, simultaneous and organic exploration of multiple cache entries. This can happen also organically, like maybe you, with a batch process, you put a lot of cache entries into the cache with the same TTL, and then suddenly they all expire at the same time. This has nothing to do with infrastructure, nothing is going on, it's just that the cache organically expired. A very good measure against this is to introduce some randomization in any TTL that you have. How bad can it get? And this is when it gets very ironical, right? Like, ironically, the more effective you do, and you as an engineer think about your cache strategy, the more pronounced this effect is, right? Due to two factors. First one is the cache hit ratio. The higher the cache hit ratio, the more pronounced this effect is. And if you have a very low cache hit ratio, the cache is actually not absorbing anything. So if it's down, it doesn't really matter so much. But if you are entering values above 90%, 90, 95, even more, which is a scenario that everyone would love to be in if you're implementing a cache-aside strategy, then suddenly you're in a much worse situation. If this, like, is usually not 101 mapping because of the issue I'm going to explain now, but 90% is usually around 10x of a spike, 95 is 20x, and it goes even higher, right? But it's not a simple stat. The second factor is the aggregation level, right? Like, when we talk about GraphQL communicating to a lot of downstream services and collecting data from them. So if you're implementing a cache-aside strategy, you usually would like to cache something that already consolidates all this data from all these services. So actually, when this is a cache miss, in this case, it's not one request that you're sending to the other service, but actually 4 or 5 or even more, because maybe you're caching a batch or something else. So the combination of these two things would actually make it a very effective cache strategy. It's actually what engineers actually try to optimize for, but this makes the situation when the cache is down worse. And so what can you do about it? So let us go quickly over these steps. The first one is make sure your application is able to function without a cache. This sounds obvious, but it's not so obvious. And as with any calculated risk or calculated downtime, you don't need it to happen in production, so you know what is the impact in your application, right? Like, you can really simulate this situation in a like, I'm not even talking about chaos engineering in production, right? I'm talking about simulating this in a non-production environment, like really turning it off and seeing how your application reacts. Or you can also implement a pre-mortem exercise where you think about how things can go badly, and it's surprising the valuable things you can discover in such an exercise. And the next ones are going to be related to how do you deal with a burst in request in any distributed system in order to avoid the cascade effect of a failure, right? The first one is implement circuit breakers to avoid talking and sending requests to a service that is already failing. Implement timeout so you don't wait forever for a request. Implement retries with back-off strategy, with an exponential back-off strategy. Ironically, if you do retries naively, you might even make the problem worse. So all like implement it with a back-off strategy and with a limited amount of retries. Like otherwise, you keep retrying forever. Use fallbacks whenever the business allows you. Instead of just failing the request when you experience higher latencies, just return a fallback value. This is like a lot of times easier than thought, right? Just return either a hard-coded value, return a value that you can get from somewhere else. Like you can discuss with your business and analyze the business requirements when this is like possible, and it's a great way of coping with downtimes. And so deduplication, don't send the same request time twice, and rate limiting, right? Like implement rate limiting. All these measures actually have nothing to do with cache aside. They really come into place when the cache is down and you have this huge burst of requests. But you should really implement all these measures on any distributed system that is communicating with other services. And finally, that's the reason of this talk. We can think of stop using the cache aside strategy, right? And this is what I'm going to be focusing on the next slides. So we prefer async communication. And when you have a service A, service B talking to each other, instead of making a call between service A and service B to get this data, what we prefer is to have an asynchronous flow where the service B, through a worker, publishes this data to a messaging platform, and then service A consumes this data asynchronously and stores it into its own local, that is the key, local data store, right? This offers a high level of decoupling, because if somehow the service B is degraded, higher latency is really down or whatever, it can happen to a service, service A is unaffected, right? It can still respond because it has everything that it needs locally. The price you're paying for this is that service A will have stale data, not up-to-date data. You need to be conscious about it. In our case, this is not like an issue, but in a lot of business cases, this is not possible. So we were doing all this for all our microservices architecture. And the question is, why were we not doing for GraphQL? Why do we have the need on GraphQL communicating with HTTP calls to the downstream services? And the reason for this was to avoid, we were thinking that it was to avoid having all the business logic in GraphQL. One of the key things that you need to take care in when you're implementing GraphQL or any gateway pattern is to really keep an eye on to avoid putting a lot of business logic in this central component, right? Like ideally, this component should be as business logic agnostic as possible and really pass through the request to the downstream services. And if it has to manipulate it, do it in a way that is as business logic as not agnostic as possible. Filter it or something like that, but not business related. So having microservices really fit with this view, right? Like you can make a call to the downstream service and just put the business logic there and not do anything with in GraphQL. But we discovered that separation of business logic isn't necessarily achieved through HTTP calls, right? Like we can achieve this also in other ways that support this async communication. So our goal is to establish an async communication with downstream services in GraphQL while keeping the business logic away from GraphQL. So this is a case where GraphQL is communicating to an API that has its own data store. On the right side, this is an independent microservice, which has a cache because we need it. What we want to do is avoid the API call and store the data locally in GraphQL without having like the business logic there. Similarly to what we do with our microservices. And the question is this possible? And I want to tell now which approach we took for this. For this, I want to talk about a concept called the write and read path. This is mentioned in this excellent book, which I highly recommend to everyone dealing with distributed systems, Designing Data-Intensive Applications, written by Martin Kleppmann. And in this book, the author speaks about this concept of write and read path and exposes what this means, which is that in a life cycle of a request, there's always a write path and a read path, and whenever we are handling data and how we are returning it to the caller. And in this example, the author puts an example of a search index, which on the write path, you have all the parts that is updating the document, tokenizing whatever we need to filter for, and saving it in the search index. And on the read path, which is the API, is receiving the search query, is parsing the query, is validating, and then it's actually executing the query on the search index. And you can see where the two paths actually meet. And why is this important for us? Because usually all APIs start like this or are actually like natively conceived in this way, right? Which is that the worker is somehow storing the data in the most straightforward way and generic way into the data store. And the API is doing all the work that it takes to return this data in the read path. It's doing all this business logic, is accumulated, the magic is accumulated on the read path. It's querying, it's filtering, it's aggregating the data. But the data itself is not actually optimized for the access pattern of this API. And this is why we put it in the cache, because it's so expensive, the read path, that like naturally, we're going to try to store it in the cache as much as we can, because we want to save this expensive path and we don't want to do it all the time. So is it possible, and this is the approach we took, of slowly starting migrating the API's flows from a read-intensive path progressively to a scenario where the read path is almost minimal and all the work is actually being done in the write path when you're actually writing the data. So let's think about it with an example. Think about it with an EPG example. EPG stands for Electronic Programming Guide. You can go into the Joyn app and open the LiveTV section. You will see a grid where the users can see the programs that are running at that specific time on LiveTV. And the user can swipe to the right and get another 3 hours view on the programs that are running, and so on and so forth. So a very simplified way of how this could be like implemented is if you have an API, an events API, that you send in 2 parameters from and to with the timestamp, and the API returns all the events that are happening in that time frame. Here the events are stored straight without further manipulation, and you can see that the read path is very big and very expensive, because this is most of the work being done in the read path, right? Like the query, the filtering of the data, like going through the entries and filtering it, is happening on the read path. And actually, and that's why we are caching it, and that's why the cache captures actually the real access pattern that you need for this, which is what? Is the bucket of this view that the users are seeing in the viewport, right? We don't need an API that gives you granular and customized filter on times. You just need an API that gives you what is on this bucket of 3 hours and give me the bucket of the next 3 hours. So if you look at the cache is actually capturing these access patterns. And our front-end engineers were actually optimizing for this because it was cached already and it was very, like responding very quickly. So can we think of a way of actually switching this and making the write path more complex and minimizing how expensive it is on the read path? And a way of doing this is actually storing the events optimized for this particular access pattern. The access pattern, as I said, is the bucket. And so you can start storing the events in the database based on the bucket they belong to with a bucket ID instead of with a timestamp that they are like occurring. This means that most of the work is actually being done now in the write path instead of the read path. The read path starts becoming very cheap and very constant in time. It doesn't matter if it hits the cache or not, because it's always very cheap. So our goal is to start moving the business logic from the read path to the write path. And by doing this, we can make the read path way cheaper. And we can avoid having a cache aside strategy. Another thing that happens when you do this is actually that the services start exposing the APIs through data and instead of request, right? Like we had this events API that is receiving a from and to parameters. And if you start making that what you store in the database is almost a one-on-one mapping with the access patterns, with the input parameters you are receiving in the API, like almost like resolving this request is almost just going to the database, finding this record and returning it, right? So it's a one-on-one mapping. And if you have this, you can start introducing a CDC handler, a change data capture handler, and exposing these entries in the database through a messaging platform. And suddenly you have your API exposed through a messaging platform instead of in request, because the entries are almost one-on-one, like one-on-one mapping to the input parameters. So how can we use and how did we use all this to dropping the cache aside pattern? And we start with this scenario where we have GraphQL communicating to an API. And we can see the business logic happening in the API and in the read path, and that's why we have to cache it. So our first goal would be, and our goal is, can we transform this and store this data locally in GraphQL? Our first step would be to move the business logic to the right path with the techniques like I showed before, trying to capture the access pattern of the API. We're going to attach the CDC handler. We're going to expose the API through our messaging platform. We are going to install a worker in GraphQL itself that consumes this messaging platform and stores this in the local data storage. This will allow us to stop using the cache aside because we don't need the cache anymore, right? It's already optimized and it's already in the database, ready to be used. We don't need the cache anymore. We can remove this, and therefore we can also remove suddenly the HTTP call to the downstream service because we don't need it anymore, and we can really get the request from the local data store. You can already appreciate here that if the other service on the right side starts going down, is degraded by any reason, GraphQL will not be affected by it because it has its own local data store and it's having the data there. This again has the cost of eventual consistency because the data will not be up to date. Great. So how did we deploy this and how did we roll this out to avoid breaking everything when we introduced this? As I said, the API was exposed also through messaging, right? So our goal was to have the same response if you're calling the service via HTTP than the message you were getting when you were importing this message into your own local data store, right? So we used this in our advantage. GraphQL has something called data sources. These are the components in the code that are in charge of actually making the request to the downstream data sources and return it to the resolvers. And we introduced here our incremental rollout. What we did first was to do a silent partial rollout and compare the two responses that we were having. This means that with the use of feature flags, we were introducing some randomization, and the request, we were still making the request to the HTTP service, but we were also sampling and some of the requests also making it to the local data store, and we were comparing these two things. And as I said, the goal was that these two responses were equivalent. And we actually found a lot of issues. We needed to turn this up and down like a lot of times. We left this running by 2 or 3 weeks, and with all the data we collected, we were realizing where we made the mistakes and which situations this was not working properly. But testing it in production with real traffic, real users in a safe way that we were not jeopardizing the real platform was very useful for us. Once we gained some confidence, we started doing some incremental traffic switch. We started on 10%, 20%, all the way up to 50%. What this allowed us was to also evaluate how this approach worked under heavy load, under different load patterns. And eventually we spiked up to 100% only under some control, under some hours for a couple of days, until we eventually switched the entire traffic to the new approach, and we were able to deprecate the actual API, like API code. So we're already approaching the end of the talk. What are some final thoughts on this approach? Access patterns matter a lot. We only implemented this on the services that were having very standardized access pattern. This usually, if you have a situation when this is not the case, this approach would be highly complex, or even probably impossible. This usually happens when users can, for example, select their input queries, can select their filters, can do some very customized queries. In that case, it's almost impossible to determine the access patterns. The classic example is a text-based search, when users can type whatever that they want. In that scenario, you need to really optimize the read path, right? And then you put all the things that you know on optimizing the read path, because you cannot apply this technique. However, the good thing is that your cache keys and entries will already show you the access patterns. Like if you're not aware which access patterns you're having, just take a look at the cache keys, right? Because ironically, if you're already having a reasonable cache hit ratio of 80%, 90%, you're probably already optimizing for your access patterns. The patterns are already there in the cache. So you can use this to actually optimize your write path and already store it in your database according to this access patterns. And on the other hand, if you have a very low cache hit ratio, you're probably caching stuff in a way that is not very efficient, right? Like you have a lot of variance in your cache keys. This is not a silver bullet. You have to be aware of the trade-offs that you're having with this approach. One of the trade-offs is that the replication has a cost. Be aware that you're replicating here the data, like as we saw it in the slides. The cost comes mainly in two flavors. First of all, the compute power that you need to replicate and the whole infrastructure that you need for the messaging platform. And the second is the storage that you have, because you start having the data duplicated in a lot of services. So you need to be aware of that and make a conscious decision on that. The write path can become very complex at some point, like as we said with the bucketing strategy on the events. Actually storing those events in the right bucket or any other write path optimization that you might have can become very complex, and keeping track of that can be very complex. You also need to be aware of that and be willing to pay that cost. And finally, eventual consistency. As I said, this comes with the flavor of eventual consistency. A lot of use cases can support and actually usually support eventual consistency. If you are unlucky to be in one of those cases that's not the case, there are other techniques that you can do for this. And this is a very interesting point, right? It doesn't actually stop in the backend. And it's actually mentioned in the book, again, highly recommendable for everyone to read. And actually, it doesn't stop in the right in the backend, the right path optimization. If you actually want to go through with this approach, you can really push these changes all the way to the front ends, right? Because you already captured the essence of what the front ends are actually requesting. And instead of stopping in the API, you can really push it through WebSockets and subscriptions like in GraphQL, and avoiding the front ends to making the request at all, right? Like you can really push it all the way through. Finally, technology and strategy differs greatly between the write and the read path. Also, the abilities that the engineering teams need in both parts of the spectrum are very different. Usually teams that are heavily focused on the right path are handling with very complex business logic, very complex codes, very complex ways of doing stuff. They're like clean code, technical debt. A lot of these aspects are very important on this part. But on the read part, actually, it comes as way more related to scalability, to resilience, and to making sure that you're delivering this data in a very safe way to the APIs that are requesting it. And the last point is this separation of data generation and data delivery. The write and read path approach matches perfectly with this idea of splitting the data generation and the delivery of data, right? As we said, we are exposing our API through data. We are generating the API as data, and that is happening on the right path, and it matches very nicely with this idea of splitting these two concepts and having the focus on these two different areas. Great, and with this, I finish the talk. Thank you, everyone, for joining it. I hope you enjoyed it, and now we can leave some space for some questions. Thank you.